Today we have Chris Little presenting at this AMOC webinar series. Chris is a staff scientist and manager of the Oceanography Group at Atmospheric and Environmental Research, Inc., where he has been since 2014. Before that, he was an associate research scholar at Princeton University, where he also received his PhD. Currently, he is the chair of the U.S. AMOC Science Team Task Team 4, which is also known as the Climate Sensitivity AMOC Climate and Ecosystems Impacts Task Team. Through this position, he also serves on the executive committee for the science team. So Chris was actually one of the first people I remember meeting when I started at US CLIBAR, where he came up and introduced himself at our sea level workshop back in 2019. So anytime sea level research is brought up, Chris's name comes to my mind, which brings me to the paper that he is presenting today, entitled The Relationship Between US East Coast Sea Level and the Atlantic Meridional Overturning Circulation, a Review. We are so happy to have you present today. Please go ahead when you are ready, Chris.
Thank you very much, and thanks to everybody else for tuning in. I know that it's a vacation week for some of us, and I appreciate you paying attention and using this time. So again, this is a paper that came out as part of a special collection sponsored by CLIBAR and the AMOC Science Team. I want to encourage everybody who's on the call to take a look at this paper, as well as the other papers in the collection, which add a lot more information about the dynamics and are very complementary. So again, thanks to everyone for making this this paper possible. I was thinking back, and I realized that I hadn't actually gotten a chance to present this as a talk anyway, and it's almost a year ago. So obviously something has happened in the interim, but I am very excited to get a chance to review some of this for myself and to present it because I think it's still relevant after looking at it a year later. So moving to the next slide, it's working. So I want to motivate the work a little bit first. Part of this is coming from the fact that climate models project enhanced 21st century dynamic sea level change, so that associated with the change in ocean circulation along the US East Coast. And you can see that in the ensemble mean of CMIP6 with this hotspot in the subpolar gyre kind of extending along the western boundary there. And it's consistent with results from models and model ensembles going back for many years. This happens or is projected in these models coincident with a reduction in the AMOC strength, so the integrated transport, depth and zonally integrated transport in the North Atlantic. That's actually shown on the y-axis of this plot, and these are new results from CMIP6 from Wire et al. So we have both of these phenomena happening over the 21st century, and we'd like to be able to understand the relationship going on in a little bit more detail, because both of these quantities exhibit a fair bit of spread across the models, indicating some sensitivity to the model formulation. You can see a hotspot in the uncertainty in the North Atlantic, and you can also see a fair bit of spread along the y-axis in this plot of AMOC strength. So is that uncertainty coming from variations in the AMOC strength, variations in AMOC components, or is it something unrelated to AMOC that's driving the spread across these different models? It would be good to have an understanding of that so that we can use that relationship potentially to constrain sea level projections, either based on the relationship between AMOC and DSL, or based on their AMOC, based on their modern state AMOC or AMOC variability. So I think that there are steps that we can take to get there, and that's part of the motivation for the paper, to look more deeply at these AMOC-DSL relationships in models, and DSL is dynamic sea level, to try to understand, using theory and some observational evidence, whether there are consistent relationships and where those relationships exist between sea level and ocean circulation. And probably most importantly, get a better understanding of the processes that underlie this covariability and their sensitivity to forcing, timescale, et cetera. So there's a second motivation going along with the looking forward, which is that we have this really extensive network of tide gauges along the North Atlantic, going back 50 or 100 years on the western boundary. And then a good network, at least in the northeast Atlantic as well, which we could use if we had a good relationship or a good sense of the relationship between AMOC and coastal sea level. We could use that in order to infer what elements of the ocean circulation are doing, what AMOC is doing, and what climate has done over the past 100 years or so. So this is a very valuable record, and we want to figure out ways to exploit it in order to infer what's going on in the climate and ocean. And people have started doing that. The plot on the right-hand side is a figure from Tal Ezra's paper in 2015, where he looked at the relationship between the sea level difference between Atlantic City and Bermuda and the relationship with rapid measurements, and then use that over the 2004 to present period to hindcast AMOC variability. That's this black line here, our low frequency component of AMOC variability going into the past. So we'd like to be able to understand how robust those hindcasts are, whether we could identify places along the coast that are the best indicators, and really understand what they're indicating. And so that's, again, another motivation to try to understand this relationship. I'll move quickly through this slide, but there are records of sea level derived from proxies that go back thousands of years. So the same thing the same reason we want to understand this relationship for tide gauges and to interpret the last century, we can also apply to look at variability in regional rates of sea level rise or regional sea level rise, and try to interpret those spatial patterns as reflecting certain aspects of climate change or AMOC variability. And with these coastal sea level records, we might have an opportunity to add additional information into reconstructions like this one from Thornelly et al., which used mostly temperature and salinity proxies and sediment size in order to reconstruct AMOC transports. So I think the only way in which we're going to be able to get robust constraints is to try to use all these different proxies that we have. And I think sea level could be very valuable if we understand what it means. So then more directly motivating this paper is just the fact that there have been a ton of papers that have come out in the past 20 or 30 years looking at the relationship between AMOC and sea level. And at least from my perspective and the co-author's perspective, it's difficult to reconcile a lot of this literature, especially in terms of what the signature, different aspects of ocean circulation and climate are on coastal sea level. And to give away one of the conclusions, I think that is largely because observational studies are focusing on shorter timescales and specific or components of AMOC. Modeling studies have focused more on longer timescales and basin scale AMOC. I think in terms of this paper, were looking, or I was looking, maybe somewhat optimistically, to reconcile these various studies. And I think what the paper ended up doing is more bringing it up and making it more explicit than in the literature to date. And in that respect, I think we succeeded, although we certainly left a lot of work to do in order to continue this reconciliation. Long motivation for the paper, which has these different components. We started off just introducing AMOC and its constituent elements. We then go through a little bit of a theoretical exercise in order to derive a geostrophic antiphase relationship between sea level along the western boundary and AMOC transport. There is so that's kind of the basis by which we move forward. Now, the geostrophic basis obviously leaves a lot in terms of assumptions that we then try to examine a little bit more in detail with observations and models. but it gives a sort of foundation for what comes next. We look at climate models and do a little bit of new analysis, which I'll get to at the end of the talk, with respect to understanding the relationship in climate models. We look at observational evidence for relationships between coastal and circulation, and then we do a lot comment on where some of these discrepancies might arise and what can be done going forward. And that's, again, really the most important aspect of this paper, I think, is trying to figure a way to resolve some of the these remaining issues and help us move forward on what I think is an topic and an important thing to understand. Okay, so briefly, we had to make a decision when we framed the paper as to whether we were just going to look at relationships with AMOC proper, so the depth and zonally integrated circulation, or look at the much more extensive literature that looks at relationships of coastal sea level and elements or components of AMOC. And if we do what we did, which is look at the relationships with components of AMOC or things that might be related to AMOC, then we have a much longer record that we can look at because as we all know, that direct monitoring is only really available since 2004. So if we look at relationships between US coastal sea level and circulation elements, we can go back much further. So for instance, this paper by Montgomery in 1938 is the first paper that we could find looking at this relationship. He used differences in coastal sea level from Charleston to Bermuda and related that to seasonal variability in the Gulf Stream and in the coastal sea level. That work's been extended recently, and I just put a couple of new studies up here, have looked at a little bit longer timescales and used the Florida cable measurements in order to relate the Florida current transport to coastal sea level, and that relationship seems to be there, although the precise scaling of it over different timescales is uncertain, but there's a reasonably robust relationship on interannual to maybe decadal timescales. Other studies have looked at longer timescales and looked at larger regions of the U.S. East Coast in order to find and found correlations with some elements of circulation that could be related to AMOC in some way over longer timescales. So the Kopp et al. Study, McCarthy et al., we're looking at longer timescales and looking at relationships along the U.S. East Coast and appear to see some correlations on decadal to multi-decadal timescales. Same sort of story for subpolar gyro heat content. So these are all aspects of the ocean circulation that might conceivably be related to AMOC in some way. Finally, there have been studies that have looked at the rapid measurements and related those to, like I said before, the Atlantic City, Bermuda sea level decrease. A study by Goddard et al. Looked at a relationship between northeast U.S. coast sea level and AMOC transport. Other people have looked at southeast U.S. coast transport. So there are a variety of different elements that have been related, and just piecing these together is it can be a little complicated because there are different timescales and they are looking at different sections of the coast. The conclusion of the paper was that the relationships are most well established over interannual and shorter timescales in locations south of Cape Hatteras, at least from the observational side of things, which is interesting because in the concept of AMOC and sea level variability in climate models is mostly focused on the northeast U.S. coast, is most over longer timescales. So that's sort of the essence of the discrepancy that we see in the or whether it's a discrepancy or not, or the essence of what we're trying to understand. Okay, so what to look at individual components of the AMOC means that we have to address the issue of coherence of these individual components with AMOC. And to some extent, we kind of kicked this question down the road. I still think it's an important question, but it wasn't really addressable in the context of this paper. I think that the point that we got to was that on decadal and longer timescales, there seems to be that some of these components are more closely related. And although that needs more work to be able to state more confidently. So a study that came out recently did this kind of exercise. This is a study by Gu et al. That looked at, in a long climate model simulation, the relationship between Florida current transport and AMOC transport. When you had both wind and buoyancy and heat forcing, that's in this control experiment, you can see a pretty strong correlation. And the correlation originates when you have the wind fixed, the correlation is driven by the buoyancy and heat fluxes, and there's not very much going on in terms of relationships between Florida current and AMOC with respect to winds. And that's kind of getting at the conclusion here, is that over longer time scales under buoyancy forcing, these things might be more closely related. But that needs more work, and it would help to do that type of work. This is a very coarse resolution climate model using some of the newer higher resolution models, which have better representation of some of these smaller scale features of the circulation. And we're just getting to the point with this new generation of models where we can actually look at decadal, multi-decadal, and longer timescales and resolve some of these circulation features and also small scale features of sea level variability along the coast. So I think we're getting to the point where we can start to assess these relationships a little bit more carefully, and also have some observations which can be used in order to assess how good a job those higher resolution models are doing. That has to be thought about in the context of looking at observed relationships is the nature of the relationship. So this study led by Chris Paikush, I want to bring up as an example of that causality issue. So we looked at New England coastal sea level averaged over these dots on the right side, and its relation to the rapid array transports. And what we find is that there is a very strong relationship, and it's very coherent at interannual timescales. But that relationship is driven, is only with the Ekman component of the rapid transport. And Chris traced this down to, by using sort of composites of negative or southward Ekman transport and positive sea level anomalies, can trace this down to an orientation of a large scale wind field. So really the anomalous southward transport is occurring at the same time as you're having wind forcing drive a locally forced sea level anomaly. And that's actually different than sort of the geostrophic argument that we put into the theoretical section. So these relationships are complicated and may have not really be causal in this respect. Caution, I'm sorry that this is ending up being kind of a cautionary tale, is that the sea level indices that we're using, so various studies have used different sea level indices, and a lot of the time they've looked at one portion of the coastline, say north of Cape Hatteras or south of Cape Hatteras, and tried to relate those directly to some element of circulation, or in some cases differenced them in order to derive an index of sea level, which can then be related to circulation. So a lot of that is based on the fact that we see this strong lack of correlation between sites south of Cape Hatteras, which are sort of down here, and north of Cape Hatteras, and coherence within those regions. So this plot shows the cross correlation of those tide gauges over the last 30 years. But if previous 30 years, we could see that, in fact, that whole area, both south of Cape Hatteras and north of Cape Hatteras, has a much stronger correlation across that divide, which indicates that this sort of coherent variability changes as a function of the time that you're looking at it at. So it brings up these questions as to what exactly this index means and what are the right regions in order to relate to certain features of circulation. And perhaps even more broadly than that, what circulation feature would have strong correlation over a 30-year period over the whole US East Coast, and then only north of Cape Hatteras afterwards. So I think these types of things are both cautionary, but it can also lead us in a direction of really trying to figure out what it is that's driving coastal sea level over the historical observed period. A little long on the observations. The modeling side of things, one of the things that we can do with models is look at the relationships between AMOC and DSL over different timescales. So I'm showing two plots which sort of illustrate that here. On the left-hand side, it's a model simulation with no wind forcing, run with with restoring to observed hydrographic conditions over 1950 to 2009. And we regress, or this paper regressed, dynamic sea level on AMOC, and you see a relationship that's very consistent with what we think about in terms of the theoretical geostrophic argument, with the antiphase relationship on the western boundary of sea level with AMOC. That's different, and I know this isn't strictly analogous, but that's different to what we see in the ensemble mean across CMET5 models, where we see more of a meridionally oriented dipole and a non-uniform or almost a dipole along the coast, or at least what's resolved in the coast by these models. And that's associated with a mean AMOC change of 4 to 5 straight. So we wanted to look a little bit more into what's going on in the individual models and whether AMOC actually explains a lot of the variance across the models. So we did this regression across models on the AMOC strength change over the 21st century. And you can see that we end up with a regression pattern that looks fairly similar to what we see in the ensemble mean. But if you figure out the amount of variance that's explained by AMOC, it's actually relatively small, which either indicates that there's some models which are doing something completely different, or that AMOC actually isn't explaining very much of the coastal sea level signature, or really the sea level variance across the models, across all the models. Quickly, sorry for going a little bit long. I hope that the points here flow naturally from what I was talking about. So observed relationships are difficult to really tie AMOC, these observational measurements in sea level. We might be able to use some models or some longer observations in order to tie those together. There is evidence that there's some for over long time scales for an antiphase relationship between models and between dynamic sea level and AMOC strength. The pattern and the amplitude is forcing timescale, location, and model dependent. So I think what we'll do is leave these paths forward up here. I think there's a lot of opportunities, and I'd love to discuss them as part of the Q&A for really tightening up these relationships and using new tools in order to understand the relationship between AMOC and sea level. And I'll just leave the thanks up here. I really appreciate all the help, and a tremendous amount of credit goes to the co-authors on this paper. So thanks, Jenny. I'll pass it back to you.
Thank you, Chris, for your presentation. So we'll take Q&A for the next 5 to 10 minutes. So if you have any questions for Chris, you can use the raise your hand button, or you can type it into the chat box. And for those who are looking for the raise your hand button, it is located next to your name under the participant list, or you can click on the little smiley icon at the bottom of your screen and it'll pull up some buttons for you to hit. All right, I see a question from Steve Griffiths. Do you want to go ahead and mute yourself?
Yeah, Chris, thanks for the talk. I was hoping to have an hour of your time here. This is kind of short because there's a lot that you were unable to say. But anyway, you mentioned that with the higher resolution models, you might start to represent processes that are more amenable to what you're seeing in the observations. Can you give a brief sense of what are those processes you think are critical? Waves, coastal waves, eddies, a little bit more detail about the physics that you're talking about that the models need to start representing better.
Yeah, I think waves and eddies, and I think that the representation of bathymetry in the coastal regions is really going to play a strong role in those dynamics. We in the paper, and this is a lot of work coming from Chris Hughes, focused on some work that he's been doing in terms of bathymetry and bottom friction as essentially things that sort of damp, attenuate, and shift the sea level signal that you see in the open ocean as you get closer to the coast. And they would point to the representation of friction and bathymetry as probably playing a large role. Again, I haven't done the work to think about it more in terms of a steady sea level, steady state sea level or mean sea level, or which I think there's some work that we could do with models to really understand what timescales are the most impacted by those sorts of things. And then the last thing is, which I didn't talk too much about in this, or I kind of alluded to in this talk, is the local forcing that occurs on the shelf. I don't know how that. I think that that can have a significant impact on coastal sea level, obviously especially over shorter timescales, wind forcing, buoyancy forcing, and I think that I can't tell, a priori which ones are going to be the most important in terms of the bottom friction and the bathymetry or the local forcing, but likely they'll be important for different aspects of the sea level variability.
Thanks.
We need an hour.
There's a comment in the chat box by Dennis Volkov that also a better representation of boundary currents. So I see a question from, I'm sorry if I mispronounced your name, Sam, is it Tifolo Diabate? Do you want to go ahead and unmute yourself?
Yeah, that's me. So hi, I'm Sam. I work on related subjects. So I was wondering, do you have a clue of what caused the shift in the correlations between tide gauges across Cape Hatteras in around 1990?
Yes, I do. I guess I left a spicy tidbit in there. So we're working on writing up the paper, but what we find is that that the annual mean correlations, which are shown there, are very strongly influenced by decadal variability. And it's that variability at the decadal timescale which is changing over the tide gauge period of record, both in amplitude and its coherence along the coastline.
Okay.
So stay tuned for more. And the paper does not spend a lot of time discussing what the mechanisms are behind that. It's so I think that's really the next question once we get done sort of documenting and doing the statistical analysis.
Okay, thanks a lot.
Yeah, thank you.
Do we have any other questions for Chris? I think we have a quiet group today. Otherwise, you were really thorough with your talk.
Yeah.
Can I ask a question? I can't see how I raise my hand. So
Yes, go ahead.
okay, Sybil and Rayfold. So aren't your results suggesting, or at least at me, that the pattern in sea level that is associated with the AMOC is quite a bit timescale dependent, especially if you look at the other side of the Atlantic at the eastern, at the northeastern part. So, and isn't that not obscuring all these correlations if you don't do this timescale separation? So, yes, this is, yeah, almost very clear here. So you have the opposite. So if we live in Europe, then we have the opposite signal, isn't it? So could you say more? Is there any theory of understanding why, what causes the timescale dependence? And if it's so strong, then how to deal with it? If you try to say this is the relation between AMOC and sea level.
Well, I mean, I think that we could do our analysis a little bit, you know, using the same model and the same forcing and look at that timescale dependence. I mean, I think that the question is whether is it really a timescale dependent relationship with AMOC, or whether other processes are coming into play when you have a sustained AMOC anomaly. I don't know whether it's heat content or steric variability or correlated forcing with the forcing that's driving the AMOC change. So I think that might be another question, is separating out the timescale dependence of, well, I mean, I think that there's probably a number of ways to go. I think the first step, you know, it's kind of with this paper, is at least to disclose and make explicit the differences, and to, especially over longer timescales, look at all the other drivers which are correlated with AMOC to try to piece out which ones are responsible for sea level variability in different portions of the U.S. East Coast, or causal. I don't know if that's a great answer, but
yeah, because I would say, so heat content is also, of course, a not only a driver but also an effect, of course, of
right.
Certainly on the long term. So yeah, you may expect a fast, some sort of wave adjustment at the coast, and then yeah, by advective and convective feedbacks that you change the heat content, and then yeah, pressure and also sea level patterns. It almost seems related that we expect an east-west gradient at geostrophy at a very short, almost immediate time scale. But many models also show a north-south pressure gradient on very long time scale. So it's probably, I would say, somehow related, but yeah, it's quite difficult to flesh it out. I agree with you.
Yeah, I mean, I think there's definitely work to be done.
But you haven't gone very far and say, well, okay, I understand how it works. So still an open question.
Yes.
Well, if we look here and the AMOC goes down, then of course our sea level scenarios almost take the long-term response from models also into account if we make scenarios. But it appears, say, if you go to the shorter time scales, and that you start with an almost opposite reaction at the European coast. So yeah, certainly for us, even more than for people in the US coast, it's very interesting to understand more how that signal evolves.
Yeah, and I mean, I didn't put this presentation figure with all the CMIP 5 models, and now there's CMIP 6 models as well, but they will give you probably a fairly different spatial pattern of sea level change than this ensemble mean relays. So it would be probably good to look back at the paper and look at some new CMIP6 results, which I think that Liu paper has some of the newest model simulations.
Okay, thank you.
Yeah, thank you.
All right, do we have any final questions for Chris before we wrap up? Okay, so we'll take this final question in the chat box from Dennis Volkov. He says, Chris, nice talk. Regarding the sea level change south and north of Cape Hatteras, can you speculate why there was no contrast between these regions before 1990?
Going back to this result, which actually isn't in this paper. I probably shouldn't have included it. I put it in a different talk, but I'm excited about it. Okay, so speculate why there's, say one more time, Jenny.
Can you speculate why there was no contrast between these regions before 1990?
Well, so there's not no contrast, but there's less than there is in the subsequent 30 years. I mean, I think that was the answer that I tried to give to the previous question, which is that the variability at decadal timescales is really important in terms of driving this annual mean cross correlation, and that variability appears to be much more coherent and stronger in this 30-year period of time. The earlier 30-year period of time. So speculating why, I think then says, well, I don't know. I think that again, this is kind of where we're leaving the analysis for now. Is what is it that changed in that 30-year period? I mean, I think that you could make hypotheses about it being some longer period modulation of the ocean or atmospheric state, and that's kind of the hypothesis that we're pursuing. Strong formulation for one at this point. Is that enough, Dennis? Okay, thanks.
He says thank you.
Yeah, that's maybe too much, maybe too little, I think.
All right, I think that'll wrap up today's AMOC webinar. So thank you so much, Chris, for your presentation. And thank you to all the participants that we had on the line. I think we had over 100 participants at one point. So the next AMOC webinar is scheduled for March 18th, and I will share details with you once it becomes available. So again, thank you so much, Chris, for your presentation.
Thanks for tuning in, everyone.